Ladies and gentlemen, friends, colleagues, it's a great pleasure for me today to announce the speaker. It's Duncan Haldane, otherwise Frederick Duncan Michael Haldane. Now I'd like to say a few words of introduction. He was born in London and is a British citizen, currently still European. He's a US resident, but what perhaps to many of us is important, that his father was a British doctor who met his future wife in Klagenfurt at the end of the war.
Solowets.
In Solowets? Ah, thank you. Very good. Who was a medical student at the time, and they essentially, his mother, Lyudmila Renko, follows his husband, her future husband, to London, where Duncan was born. By his own account, he considers himself half Scot, half Slovene.
Correct.
Which is especially, we can be proud of that. He was educated in London and Cambridge. He was awarded a Bachelor of Arts degree at Cambridge in 1978. And in 1978, he was awarded a PhD, which with Philip Anderson, himself Nobel Prize winner, just a few years before that.
About a few weeks before that.
Oh, right. So you got an award in spite of that? Or Okay. Professor Haldane has started his career in France, in Grenoble, Institut Langevin, and became an assistant professor at the University of Southern California in Los Angeles, where he remained until '87. In July '86, he joined the physics department at the University of California in San Diego, where he remained for, I guess, 6 years. And in 1990, he was appointed professor of physics at the Department of Physics at Princeton University, where he still remains today. Professor Haldane is known for a wide variety of fundamental contributions to condensed matter physics, including theory of Luttinger liquids, theory of one-dimensional spin chains, the theory of fractional quantum Hall-Effect, exclusion statistics, entanglement spectra. And since 2001, he's been developing a geometric description of the fractional Hall-Effect, which we've heard something about yesterday. Haldane was elected a Fellow of Royal Society and a Fellow of American Academy of Arts and Sciences, a Fellow of the American Physical Society, a Fellow of the Institute of Physics, a Fellow of the American Association for the Advancement of Science. He was also awarded the Oliver Buckley Prize by the American Physical Society, the Alfred Sloan Foundation Research Fellowship, Lorentz Chair, and a Dirac Medal. In 2016, he shared the Nobel Prize in Physics with David Thouless and Michael Kosterlitz for theoretical discoveries of topological phase transitions and topological phases of matter. Today's talk is entitled Entanglement, Einstein's Guide to Quantum Mechanics, and I think it's about time that I stop.
Okay, thank you very much. Okay, Dobar dan. It's a great pleasure to be here at Joseph Stefan Institute. This is a talk that's aimed at, you don't need to know physics or quantum mechanics for it. So I'm going to tell you a little bit about the history of entanglement, which is a very, was introduced by Einstein as a property of quantum mechanics that was so strange it couldn't possibly be true, but turned out to be quite central to the recent discoveries of these new kinds of topological states of matter. They're basically, interestingly, topologically entangled states of matter. So, okay, so let me move on. So, as I say, in public, this is a public lecture. So it's aimed, hopefully, one learns at least one thing in a public lecture. So, of course, quantum mechanics is always a difficult subject. In some sense, it's more difficult than relativity with business about clocks. Quantum mechanics has got issues about measurement, and it's, in some sense, difficult for both the public and the scientists to understand. We don't really, but we work with quantum mechanics, and it's the theory, it's the correct description as far as we know of the world around us. So usually in a public talk about quantum mechanics, the subject that's brought up is the Heisenberg uncertainty principle, about that you cannot simultaneously measure the position and velocity of a particle, or more generally, by measuring something, you affect it. And this has flown over into all kinds of areas, like economists talk about. If you try to measure something economically, you will affect it. But I'm not going to talk about the usual system. I'm going to bring up first two basic other key ingredients of the quantum theory, which become related, which is the Pauli exclusion principle for electrons, and this entanglement property, which was first pointed out by Einstein, Podolsky, and Rosen in 1935 as an attempt to really show that quantum mechanics couldn't possibly be true. Okay, and of course Einstein is well known for all kinds of important things. Einstein seems to have it looks like he likes his big achievements in years ending in 5, because he seems to have a 10-year cycle of things starting. And of course, Einstein is known for all kinds of things, mainly for relativity and his geometric theory of gravity, which, of course, the last Nobel Prize was finally for the direct observation of the gravity waves that were predicted. But of course, it's probably not so familiar that Einstein actually got his Nobel Prize for nothing to do with relativity. He got it for his early contributions to quantum mechanics and his understanding of the energy gap in the photoelectric effect. When you shine light on metals, it ejects electrons, provided the photon of light has a sufficient energy to kick the electron out. And of course, that's how garage door, the device to prevent your automatic garage door from chopping your head off, is based on, if you walk in front of the light beam that gives the photoelectric effect, it stops and reverses the door. So Einstein very famously, when in his gravity theory, he introduced this cosmological constant. He wanted to have the universe be static, because somehow the equations predicted the universe that would either be expanding or contracting, and that looked like there was a beginning of time, maybe a creation, which sounded a bit religious. So the prejudice at the time was to make the thing look static, so the universe would be always the same at all times. So he introduced the cosmological constant. But about 2 or 3 years later, Hubble discovered that the universe was expanding, and Einstein very famously said that this was his biggest mistake. But of course, Einstein's mistakes have always been incredibly useful. And the biggest mistake is probably, of course, only about 10 or 15 years ago, we discovered that the universe was actually accelerating. There was a kind of anti-gravity force, which is probably the vacuum energy contribution to the stress-energy tensor. But so, of course, there's still a kind of puzzle about why the cosmological constant should be so small and things. But basically, people mainly believe that the so-called dark energy that was discovered is really the Einstein constant. So his mistake is definitely not such a mistake. And in quantum mechanics, again, from 1905, he actually had, of course, the famous 3 things. Photoelectric effect, special relativity, and Brownian motion. 1915, the gravity. 1925, another contribution to quantum mechanics, the Bose-Einstein condensation, which of course has also led to Nobel Prizes in studying cold atom gases, which exhibit this. I guess 10 years later, but 10 years later, in 1935, he'd become disenchanted with quantum mechanics. And what one might call his second biggest mistake was he pointed out the property of entanglement, which I'll describe, which he thought was so strange. He called it spooky action at a distance. It said it was so strange. When it was eventually measured or attempted to be measured, it would surely show that quantum mechanics was wrong. Well, of course, we now know that when it eventually did get measured experimentally, well after Einstein had died, quantum mechanics passed the test with 100% marks. But of course, before Einstein, it hadn't really been realized how important this entanglement property was. And in recent years, entanglement has actually moved from a very philosophical thing to a central part of quantum mechanics. And now it's believed, people talk about entanglement as the fuel which may drive future quantum information processes. So one can say that, one could call this his second biggest mistake, but it's been incredibly useful that he did this, even if his motivation turned out to be incorrect. Okay. And as I say, this is the story. He called this spukhafte Fernwirkung in German, which probably translates as spooky action at a distance. Schrödinger came up with the word, I think the German is Verschränkung. I'm not sure what it is in Slovenian. France, it's intrication, so every language seems to have found a different word for entanglement. But anyway, this is the word we use, and Schrödinger went into it a bit further. So, as I say, he thought pointing this out would show that quantum mechanics was wrong, and that's not what happened. So as I say, quantum mechanics has always been a very mysterious property for the public, more than relativity. And as I say, for a working physicist, I don't worry about whether quantum mechanics is correct or not, or what measurement means. I kind of use quantum mechanics. But as I say, we know it's confirmed to be the true description of the world. And the more simpler classical mechanics description from earlier times that we intuitively feel and use in our daily life should be viewed as a very good approximation to quantum mechanics on scales much larger than atoms. So as I say, originally Einstein's objections seem very philosophical. I mean, part of the issue of the entanglement and Einstein-Podolsky-Rosen paradox is some experimentalist has to take a decision about which polarization of a light or which direction of a spin he should try to measure. And then you start coming up with issues. Was the experimentalist, was this an action of free will, or was in fact the direction he was going to choose to do his measurement preordained in history? So all kinds of questions that philosophers like to debate. Is quantum mechanics compatible with free will? Well, this is not the kind of question that a working scientist finds very useful. It can be debated, a great thing, but as I say, today entanglement is no longer a philosophical issue, but it's experimentally confirmed, and it's on its way to having technological importance. So we've moved from philosophy to an empty talk in some way to using things, right? So, an important property of quantum mechanics, as I said, is the Pauli principle, which says that two particles of the type that we call fermions, there are two kinds of particles. Basically, most of matter is made of fermions, basically, although gluing two fermions together makes a boson. But the elementary particles like fermions, electrons, can't be in the same state, which roughly means, roughly speaking, can't be in the same place at the same time in a similar state. Okay, so I think in a public lecture one always likes to give the people who have, everyone should come away knowing something new. So this is the question, the question often is, where does quantum mechanics affect us in our daily life? And one big answer, which comes from the Pauli principle, is we don't fall through the floor. After all, gravity is pulling us downwards towards the center of the Earth, and the atoms which we're all made of, which are built up into the molecules, are over 99.9% empty space. So why don't we just fall through the center of the floor? And the answer is, of course, Newton gave a simple answer. He said there was a normal force, which is a kind of practical observation. But the quantum mechanics is responsible for the force that prevents us from falling through the floor. So I'd say in the kind of everyday language that Newton invented, the explanation would be as follows. Here is Einstein, or standing on the floor. He's actually got 2 feet on the floor, so he's got a gravity weight pulling him from his center of mass, which is, I guess, where if he had a large meal or something, it'd be there, and it pulls him down towards the floor with mg, and there are 2 forces, one from each of the soles of his feet, exerted on the shoe by the floor, which point upwards, and these are the so-called normal force. And in high school, everyone learns a little bit of mechanics, so they know that every force has a reaction equal and opposite to it, etc. And then if you were doing high school physics, you would have to write down the balance of force equation that n1 plus n2, which ought to be vectors, I suppose, or pointing upwards, minus mg downwards is 0. So that's Newton's explanation of why we don't fall through the floor. And that was, of course, an empirical fact. He noticed that you didn't fall through the floor and said, well, there has to be this normal force, right? But, of course, he didn't explain what the normal force was. And, in fact, the normal force is basically the result of the Pauli exclusion principle. And from the quantum mechanical viewpoint, you have a load of atoms, the centers of atoms, the nuclei, or maybe the ionic cores of the atoms, are bound together. They hold together by kind of molecular glue or whatever in the soles of your shoes, and there's another set bound together to make up the structure of the wood. But some electrons, the outer electrons that are bound to these things, go around, and these sets of electrons in the shoe can't be in the same place as the electrons from the floor. By quantum mechanical, Pauli exclusion principle prevents them from entering the space occupied by the electrons of the floor, and that means that at the line of contact between the two materials, there is a force that excludes them. So in that sense, quantum mechanics is present in our everyday life and responsible for everything around us, but we don't really... until this last century, we didn't really think of it as quantum. We didn't realize what was going on. In fact, no one understood what atoms were until quantum mechanics. You couldn't understand what an atom was or how it worked or whatever until quantum mechanics was created as a thing. Okay. So as I say, one of the fundamental ingredients of matter that makes us all up, or makes, in fact, of course, normal matter is, now we know, is only some tiny fraction of the percent of the energy in the universe. So there's all kinds of other matter which we don't understand, dark matter, etc. But normal matter, the fundamental ingredient that holds normal matter together is the chemical bond, which, of course, in fact, does involve two electrons, which are basically in the same place. Two electrons halfway between a pair of atoms acts as a kind of glue that glues them together. So actually, this is apparently a contradiction to Pauli's statement, but of course, actually, Pauli, at the same time as discovering his principle, it also solved the problem. He realized there had to be an additional degree of freedom, an additional thing you needed to describe about the electron, which was not just where it was, but also its property called its spin. So the quantum state of an electron doesn't just involve the position and the speed, but also an internal degree of freedom, which we call its spin, in analogy to a little spinning top. So an electron is, of course, a charged particle, but a charged particle with a little magnetic moment due to an angular momentum, an intrinsic angular momentum that we call spin. And of course, from this viewpoint, the periodic table was explained because you build up the things by putting two electrons in each state, one in up spin and one in down spin. And of course, now we've gone from this old... There was a previous, before Pauli, in around 1912, there was this old Bohr picture of an atom, which was like a little planetary system with a sun at the nucleus at the middle and little elliptical orbits of atoms. And this is still perhaps the general public picture of an atom, because this cartoon picture from 1912 is around everywhere. Of course, this is what an atom... Atoms now, you can really see them, and if you put the electron states into a very large orbit, which in this picture would be like Pluto or something like that, a so-called Rydberg orbit, you can actually now image the electron in atoms. So this is actually a real image of a hydrogen atom with the electron around it excited into a so-called Rydberg state with a number of about 100 orbitals up from the ground state. But then it's big enough for you to actually image and see these things. So this is a better picture of a quantum mechanical atom, because the electron forms a kind of fuzzy cloud rather than these little orbits around the system. Okay. So anyway, the chemical bond, here's the spin of the electron. The chemical bond is made of two electrons with exactly opposite spin, so they can occupy the same space in space, roughly speaking, they can occupy the position at the center between these two ions, and the electric force then glues them together. But the big issue here is whatever the direction of electron 1 has, if its spin is a little direction given by the right-hand rule, it's actually spinning in one way, or you point the spin along your thumb, right? The other electron has to be pointing in the opposite direction, because otherwise it couldn't be in the same place. And if you make a slightly better picture of that, the electrons actually, there's no particular direction to the spin of one electron. It's just the two electrons always have opposite direction spins. And of course, in quantum mechanics, a quantum state is actually presented by a complex number, and the electrons have this Fermion principle. The principle that prevents two electrons being in the same state, in the same place, means that if I swap the two electrons around, this quantum mechanical state changes sign. It's actually a complex number, but it flips its sign. So it's up, down, minus, down, up. And if these were both up, then up, up, minus up, up would cancel and be 0, which is the Pauli principle, right? But of course, it doesn't have to be up, 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 down, plus down, up. It could be 45 degrees. It could be this kind of slanted thing, or it could be sideways. The basic thing is that the state is odd. It changes sign if you swap the two electrons. So the quantum mechanical state, this is actually the poster child for entanglement. The electrons are fundamentally entangled because it's not that particle 1 is up and particle 2 is down. They have the state that whichever direction one is in, the other is in the opposite one. And so there has to be two components to this thing. So of course, the length of the chemical bond is about 1/10 of a nanometer, and 1 billion nanometers is a meter. And I've given this talk in the United States, so I do have to translate what a meter is. On this length scale, on the length scale of the molecular bond, the two electrons are in this completely entangled state. And what Einstein worried about was, suppose, at least a thought experiment, because he loved to do thought experiments, was what would happen if I took this chemical bond and stretched it and stretched it and stretched it without disturbing it, and let the distance be, not just a nanometer, but a meter or a light year, right? Kilometers, light years, right? And he thought the consequences of the fact that whatever this electron spin was doing, this one would be the opposite, would violate the principles of causality in relativity. Abstract thought experiment possibility that the chemical bond would be stretched. Now, of course, when the electrons are close together, the entangled state of the two electrons in the bond it's got a large binding energy, which is the energy that causes matter to be stable and wants to clump together to form interesting arrangements, such as us, for example. And this is because there's quantum mechanics, one of the principles, in fact, that one of the things that Einstein discovered in the photoelectric effect of 1905 was that there's an energy gap. There can be only a set of certain allowed energies in quantum mechanics, and the chemical bond is protected by an energy gap that lowers the energy of the pair of electrons in this entangled state to be lower than relative to other possible states they can be in. And that's, of course, why ultraviolet sunlight is bad for your skin, because it's enough energy to break some of the bonds in your skin and, have bits and pieces flowing around that can give you skin cancer and stuff. But if you just regular heat from an infrared lamp is not going to break the chemical bonds. So that's why it's bad for you to go to these tanning saloons and get too much ultraviolet, to break too many of your chemical bonds, but there's a protection. Now, if I pull this bond apart so it's very largely separated, this is a very unusual situation because it becomes extremely fragile. The more you stretch it, the more you lose this energy gap that protects it, and so a tremendously stretched chemical bond where the spins are in this, I put a dotted line rather than up, down, minus down, up. So the dotted line means they're entangled in this singlet state. This thing is very fragile against what we call decoherence. That it can be disturbed by another electron in the environment here, and instead of being entangled with this, it'll lose its entanglement with the distant electron, and it'll become entangled with its local environment. And this is actually the basic problem that people are trying to defeat to make quantum information a reality, quantum information processing a reality, because if you store information in entanglement, you have to worry about its decoherence, its degradation by interaction with the environment. Okay. So I say Einstein, Podolsky, and Rosen, they thought of the origin of what we now call this an EPR pair after them, of widely separated particles in this entangled state. They thought it could be made by decaying an initial kind of confined state, somehow switching off the binding process that makes the chemical bond. But you can think of it, if I put a pair of these particles in the box, which are entangled, they're kind of locally there, and switch the walls of the box off, which is actually the kind of experiment people do with cold atoms now. They hold the atoms in a magnetic trap, making this box, and then actually this is the kind of experiment that they do. They switch the box off and everything flies apart, and then they measure what happens. Well, in this EPR experiment, you switch the box off. You can see there's a principle of conservation of momentum, that the motion of the electrons has to balance. If one electron is moving one way, the other's moving the other way, and they're continually bouncing off the walls of the box. But once you open the thing up, they're going to fly apart, and whichever direction electron 1 flows in, the other one will always be going in the opposite direction because of this conservation of momentum. Some momentum that direction, and that one has to add up. So the Einstein, Podolsky, Rosen, you somehow do something, and these electrons fly apart. So as long as they don't get entangled with anything along the way, they will maintain this up down minus down up structure. And so in principle, they could go to large distances. Now, electrons have quite a big tendency to interact, and in fact, let me say. So actually, interestingly, Einstein EPR, and this was announced in the paper, this Einstein attack on quantum mechanics was front page news in 1935. I guess, Hitler hadn't invaded anything that day or whatever, so there was simply, it's unlike, it must have been no news on that day for it to make the headlines of the newspaper. But in fact, apparently, Podolsky, Einstein was extremely angry apparently about it, I was told. Podolsky went to the papers with this, and Einstein thought this was more of the physicists shouldn't be washing their dirty linen in public, right? So they should keep this in the physics community. But Podolsky went and broadcasted it, and it became, because of Einstein's fame, it became famous. So his worry was, suppose I make a measurement of the direction of the particle. According to quantum mechanics, until the measurement was made, the particle's spin could be pointing in any direction. And the statement was, when you did the measurement, and whatever the experimentalist selects some direction to measure the spin along. And the point was that the experimentalist decided to measure it this way, it would immediately cause the result of a measurement on the other spin to be in the other direction. And this seemed to Einstein to be a violation of the principle of causality that says, things can't communicate instantaneously. Somehow the electron was communicating the fact, according to quantum mechanics, the electron was somehow communicating the fact it had been measured to the other electron, which could be a very long way away. And the point was, the choice of the measurement axis was up to the experimentalist. You could choose it that way, or up and down. And Einstein felt that couldn't possibly be true. He felt that the electron had the direction of the spin of the electron had to be chosen already when the box was opened, right? He couldn't accept that it didn't get chosen until the measurement was made. So he thought there was some hidden variable somewhere that he called it local reality. He said that quantum mechanics violates local reality, whatever that means. So as I say, if both observers do the measurement, they'll get the opposite result, and they have to make a choice of the measurement. And okay, suppose they only agree to make the choice of which axis to measure till well after the particles have split. This is where the whole issue of the free will came into it, right? And basically Einstein made this famous statement, which presumably was in German, that God does not play dice, and that he said this can't possibly be correct. And the basic issue was the result of the. So he felt his point was the result of the experiment had to have been determined at the moment the electrons flew apart, and it couldn't possibly be sensibly determined after that. Well, as I say, he incorrectly thought that if this test was eventually done, and again he thought it would be a long time in the future, it would definitely show that the particle spin was already determined when they split, and that quantum mechanics was some approximation to a true microscopic description of the universe, which obeyed local realism. But as I say, other people thought about this, and David Bohm. People started reformulating a more precise form of the EPR experiment, and probably John Bell probably made in the 60s, late 60s. John Bell probably he crystallized. He made a very precise kind of test of a measurement that couldn't possibly be compatible with with local realism, although the whole issue of free will is still in there as the only possible tiny little place to squeeze for the anti-quantum mechanical people to squeeze out of Bell theorems. And in fact, in 1982, the French physicist Alain Aspect finally did these experiments, and the experiments showed full violation of local reality according to Bell theorems, and quantum mechanics essentially got this 100% correct mark after that. Now, electrons are kind of tricky to work with because they're charged and they kind of like to interact with the environment, but we know that photons can travel, photons which were created, a few 100,000 years after the Big Bang, and have continued towards us unaffected since then, so we can look back and see, look back till recombination to see the universe. So photons can travel a huge distance and with avoiding entanglement with the environment, and the test was actually done with the photons. Sorry, here we are. So in fact, instead of spins up and down, it was two polarizations of light. And light you can either look in vertical or horizontal polarization, which is what your sunglasses are doing to get rid of glare, or something slightly more like spin is the photon can be put in circularly polarized states, which are one way or the other way. And in fact, since I wrote this slides, I say the people have now shown EPR pairs separated. They started off with Lake Geneva. Now it's across oceans. The Chinese have done it to satellites in orbit. The next thing is going to be at the Lagrange points between the Earth and the Moon. They'll put some senders in there. So we actually can see these EPR photons. And of course, some of the early applications of quantum information ideas is to show how you can send your codes for your cryptography codes could be sent in a way that you could in principle tell whether they'd been intercepted. You go from Alice to Bob, and there's Eve in the middle who's trying to read it. And if Eve manages to read the code, then you can tell that she read it because the quantum mechanical state is ruined, etc. So, as I say, the era of discovering what kind of cool things can be done with quantum mechanics is what's started now, right? What we're starting to find out from all this stuff is that we're trying to gain a direct control of quantum states. In the past, experiments were usually equivalent to bashing something with a hammer and seeing what pieces flew away. Now we're trying to kind of manipulate quantum states more like by gradually nudging them in some directions to avoid kind of doing what we call a measurement, but just gradually change them and store information in it. And what we're actually finding is that quantum mechanics allows many, many strange things that we didn't really imagine possible to happen. And in fact, one of the new ingredients in what people are now talking about a second quantum revolution, the first one being 1928 to 32, we're kind of starting to actually bring in a lot of these ideas which were really stimulated by EPR and entanglement in quantum information theory, and try and get a deeper control of quantum states. And it's quite plausible that this is going to lead to interesting new technologies as we gain an understanding in the next century. Okay. So as I say, classical information, as opposed to quantum information, it was stored in a bit, right? Which is a number. A bit is really a switch which can be on or off, a 1 or a 0. And so there's my switch. A switch could be determining a large number of spins in a magnetic material. The spins of the electrons like to line up positive. At least some of the electrons want to line up with all their spins in the same direction. So a little piece of iron will have magnetized in a certain direction, and will have all the conduction electron spins will be pointing one way. And if I flip the direction of this magnetic domain, they'll be pointing the other way. So this is a classical switch, which could be thought of as a large amount of electrons with their spin in one direction, and the other state is a large amount of electrons with their spin in the other direction. But quantum information is stored in the state of a single spin, a qubit, which you then have to read by a measurement, which requires you to make a choice of measurement axis. And the basic point is that in the quantum, the spin actually can be pointing in any direction, right? And so the information that can be stored in the qubit is not just up or down, because the axis on which you decide to measure is your choice in some way. The spin can actually point in any direction, and they call this a Bloch sphere. And at least from this picture, the information is stored in a complex number which represents an amplitude, but clearly there's more information you can store by the direction in which the spin is pointing in than up or down. And that's the secret of where the extra quantum information can be stored. Okay, so what has this got to do with topological quantum matter, which is the work I did and others did? And as I say, to the best of our knowledge, the basic laws of quantum mechanics were established during the first quantum revolution. Maybe the first one was actually the second one, because there was this early quantum mechanics around 1912 or so due to Bohr, which came up with this little planetary picture of the atom. But Bohr's theory is a cartoon. The quantum mechanics that was found between 1928 and 1932 basically cleaned up a full and correct account of atomic physics, nuclear physics, all this stuff. So all these kind of developments later are all just applied quantum mechanics. The basic rules were found then. And the basic point is, just because we know the laws of quantum mechanics doesn't mean that we know everything that's allowed to happen. In fact, the same thing comes with electromagnetism. Maxwell finished the Maxwell equations around 1870 or so. And once you've written down Maxwell's equations, you've basically written down everything about electromagnetism is in there, right? But of course, how smartphones and X-rays and all kinds of things work, is a lot more than just writing down the Maxwell's equations. And in fact, when Maxwell presented his equations, there's a famous conversation he had with Gladstone before Gladstone became Prime Minister in England, when he was a lesser minister. He said, Professor Maxwell, what use is all this? And Mr. Maxwell replied, Minister, I can't tell you right now, but I can tell you for sure that one day you will be taxing it. So of course we know that electromagnetism really created a fantastic new technology, but it took quite a long time to understand. For example, in electromagnetism, photonic crystals and things were only kind of even conceived of in the 1990s, and manipulating the flow of light with very interesting things. So there's still developments going on in electromagnetism that we didn't know. So quantum mechanics. So as I say, around 1980, condensed matter physicists, and condensed matter is just a fancy, it used to be called solid state physics, but when the transistor was invented, all the kind of transistor radios had solid state written on it. It was very proud that they had solid state components. So everyone thought you were working on transistor radios if you were a solid state physicist. So they incorporated liquids in it and changed the name to condensed matter, which means atoms that are clumping together under the forces that bind together by various forces, quantum mechanical forces or whatever, as opposed to gases where they're all moving around separately, right? So as I say, people thought they had a basic understanding of condensed matter physics by 1980, and this is all the stuff I learnt when I was a student. But independently around that time, two kind of weird properties, unexpected properties were found, and these turn out to be properties of new kinds of states of condensed matter, which quantum mechanical entanglement plays a much larger, a key role in a way that it doesn't in the more normal states of matter. And you can view this as two tips. So initially, one was some work on magnetism that I discovered around 1980, and almost about the same time, Klaus von Klitzing experimentally discovered the quantum Hall-Effect, which, if I have time, I'll get to. And these were initially had no obvious connection of any kind between the two, but they both turn out to be early examples of this new kind of topological matter that really hadn't been guessed at before they were found. So this was a theoretical discovery, and this was an experimental discovery. Both of them were unexpected. But now you could view this as this metaphor of the iceberg, because since then, many more kinds of topological quantum matter were found, particularly in the last decade, and all kinds of interesting, much more interesting parts of it have come to light, which could be useful for the quantum information thing. So topological matter, what does that mean? Topological matter differs from ordinary matter because the entanglement properties that it has actually can be described by like whole numbers, integers, like -1, 2, 5, 3. From this viewpoint, ordinary matter would be described by a boring number, and I've actually been rebuked for this because a mathematician said the number 0 is not a boring number at all. It took a long time to discover, but basically the number 0 was not known until, I guess, the Arabs or something. But anyway, simple numbers like 1 or 0 with an ordinary matter, while more exotic numbers describe the topological matter. And the basic point is that whole numbers can't just change continuously, right? The whole number has to jump. From 1 to 2 is a jump. You can't go continuously from 1 to 2 and stay a whole number. You can go from 1 to 1.3, 1.35, but if you're forced to be a whole number, you've got to change. So if the matter is described by, has some property which you could label by a whole number, then there has to be something interesting at the boundary between the topological matter and the normal matter. And it turned out to be one of the very characteristic things of topological matter was that it had something interesting going on the boundary between it and normal matter. So regular matter we'd understood by 1980. We'd understood crystals. In crystals, the atoms inside a crystal form some regular little pattern in what's called the unit cell, and then these things are stacked together to form a nice regular array. And people study this. This has something called broken symmetry. Clearly, I can't just move sideways by an arbitrary amount. I can only move sideways by a discrete jump. And this thing has also broken rotational symmetry. If I rotate, it's different. So all the work prior to this had focused on the properties we call broken symmetry, which was the basic understanding of interesting parts of matter, crystals and things, and superconductors. And in this thing, nothing special is particularly associated with the edge. While the quantum Hall effect, or the spin chains, they have a feature that something interesting is going on at the boundary. And in fact, in the quantum Hall effect, it's very interesting. There's information or states can travel only in one direction around the boundary, which is quite surprising, kind of like a one-way street. But in the bulk, we have something we call a topologically ordered liquid. And by looking at it, it's got no broken symmetries. There's no symmetry difference that between the inside and the outside, but there's this topological difference which requires something funny to happen at the boundary. And as I say, unusual excitations are kind of sort of inevitably present, almost inevitably present at the boundary between this topological matter and regular matters. As I say, the whole number can't change continuously, and that means that topological matter that has a much greater stability than its properties are very stable in a sense, because if I remember how you make a chip for a computer, this silicon wafer has to be created in an extremely clean room. You've probably seen pictures of people in these space suits. Basically, one little speck of dust from your hair, a little bit of dandruff or something will fall on the chip. It's completely gone. You have to throw it away. So you have to take incredible precautions to make everything clean, because a little bit of dirt will ruin this nice, beautiful silicon wafer and make the computer chip not work. But if the property depends on a whole number, you actually have to do a significant amount of damage to change it. So a little bit of damage cannot change the topological property. So you've got in principle at least, there is a threshold. You have to damage it sufficiently badly to change it. Now the classical example of topology, which the people at the Nobel press announcement were trying to explain all this stuff to the public is the theory of the number of holes. In mathematics, topology is a classification, started off as a classification of closed surfaces by number of holes, and this leads to this issue of donuts and bagels and things. And basically a shape with a sphere or a ball has no holes. It can easily be distorted. You can change a European soccer ball, you can squeeze it and make it look like a rugby ball or an American football, whatever it is, by squashing it. But it doesn't change the number of holes. To make a hole in it, you've got to do a really significant amount of damage to punch a hole through the ball and change it to a donut shape. And basically, holes are topological objects because you can't say I've got 0.36 of a hole. You've either got one hole or no holes or three holes, right? And so geometric properties such as curvature of the surfaces are local properties, but the amazing thing that Carl Friedrich Gauss discovered was that integrals over local properties can actually characterize the global topology. By studying carefully the surface, you can actually count the number of holes. And actually, Gauss discovered many amazing mathematical properties, but this one I think he believed was the strangest and most important thing that he found. He has a Latin name for it, the Teorema Euclidiana or something. And this is the so-called Gauss-Bonnet theorem, which for a high school student it seems kind of trivial. You all learn in high school that the surface area of a sphere is 4 pi r squared. And Gauss's curvature is a product of the radio of curvature, which for the sphere are equal in both directions, so it's just 1 over r squared. So Gauss's theorem just tells you that 4 pi r squared times 1 over r squared is 4 pi. Now, the amazing thing that Gauss discovered was, while this detail of this integral changes completely as I start to distort the sphere into a football or a banana or whatever, this number doesn't change. So long as I don't make a hole in the system, you still get 4 pi. So this is an easy homework for a high school student, but if I gave you the sphere as a banana shape, it would be a very challenging piece of mathematical calculus to verify that. And of course, a sneaky teacher could have given this as a homework problem. He had very easy grading of the homework to do because he'd know the answer was only 4 pi or whatever it was, depending on the thing. So it's a trivial statement for a sphere, but non-trivial for another manifold. And this is the famous business about the coffee cups. So the ball is topologically equivalent to a mug with no handles. The bagel has got equivalent to the coffee cup with 1 handle. This thing is called a loving cup. It's got 2 handles. I guess 2 people can share it or something. And this was apparently, they invented something called a Swedish pretzel, which really is a Santa Lucia bun, but in actuality, the holes in the middle get filled up when they bake it, so it doesn't actually look like that. This is the so-called German pretzel, where the number works out 8 pi, And they actually do find some objects like this. I didn't actually know what the name of this is, but someone suggested this should be called a California loving cup. Anyway. So, as I say, before 1980, topological quantum matter was unknown, and then we found this stuff. And as I say, it took a long time to understand that, but we're finally achieving a thing. So I'm not sure how much time I have, so I maybe want to skip over a few things. But as I say, it turned out that quantum entanglement was a key thing, and the topology was related to entanglement. So if things are trivially entangled, you can cut them in half, and there's no connection between this side and that side. Entanglement, if they're not entangled, it means if I measure something in this side of the system, it won't affect anything that happens on the other side. Okay, but for the topological matter, which has this kind of edge state to it, if I try to cut the thing in half, I pull it. It's initially a bit difficult to pull it. I'd say you have to do a significant amount of damage before you actually change the topology. So it's starting to resist a bit, but suddenly you pull it apart, and then the things are separated. But now the entanglement got replaced. In some sense, the entanglement between the two had to terminate on something, and that's what causes these edge states to be there. So it's a bit like you try to break a bar magnet into two. You want to separate the North Pole and the South Pole, but by the time you separated it, you've still got a new South Pole and a new North Pole on each of the magnets. So the entanglement, which used to go all the way through from one side to the other, is broken, but it has to terminate on something, and that creates these new unexpected edge states, right? So the topological states of insulated matter can in principle be assembled by bringing the matter together, just bringing atoms together. And if it forms a topological state, something has to happen on the way as you bring the atoms together to form this material, and that's where this thing happens. And in fact, once something's known, you actually can go back and find it should have been discovered earlier, right? A lot of things that get discovered, there may be some funny little detail here, and no one realized the importance of the general principles behind. And in fact, you can go back to calculations in 1939 by Shockley, who actually went on to invent the transistor at Bell Labs. But you bring this kind of toy model of atoms together, and they manage to do some kind of calculation, and you bring the atoms together and calculate their energy levels and things. When they're widely separated, they're just discrete energy levels of an atom. This is a toy model atom in one dimension. But as you bring them together, you see something happens, and these bands form which join up, and they split apart, but they leave interesting states which turn out to be the edge states behind. And so this actually is essentially today's topological insulator that got discovered in 2006. This is actually a crystalline topology, a symmetry-protected topological insulator. But so the interesting principle is that, you find this stuff. And let's skip some of this. Okay, so one of the interesting things you see in the thing is that if you fill the electron levels up, you have to fill them up to a point in between, which is called the Fermi level, or the chemical potential. So if there's one electron per atom, the chemical potential would be here. If you go through here, it would have to be trapped in this tiny little gap between these two states. So most likely it'll be down here, where one electron is lost from the system, or another electron is added to the system up here. And then where did that other electron go? It actually went into the system, but half of it went onto one end and half went to the other end. So one of the typical weird things you see in topological matter is the electron, which we think of as an individual particle, can actually get split into fractional pieces. And in fact, I was being told interesting experiments going on here that could possibly be fractional charges in some interesting compounds. But so for example, in a spin chain or whatever, you can have one electron in every site, and you break things up and pull an electron out, and then this object can split into two. So one of the typical things you see in topological states is fractionalization. Okay. So as I say, in heavier atoms, electrons So what I found, let me just go, one of the things I found, I'll quickly go through a few things. The electron, magnetic atoms, the spins in the electrons, well, you don't form an entangled state with the spins, you put them in parallel to each other and they line up and they form the elementary spin is the spin of the electron, and you can, which is formally called a half. It's a half integer angular momentum, and you add them up together, and the spin is 2s of these things added together to make a spin s. And the basic thing is the spins that go into the atom, there has to be a whole number of them. And the big difference, when I discovered it mattered whether it was a whole number was even or odd, and that's what people hadn't decided before, and it turned out to be because of this topological entanglement property. So in 1981, I discovered the spin 1 chain could have a novel property. The previous expected state of the system, it was something called an antiferromagnet, where the spins, the magnetic moment, the direction of the spins is equal and opposite on neighboring atoms. So they kind of look like that. So this was the kind of expected state. This is an interesting state with long-range order. It's got a broken symmetry that if I translate by 1 unit, it's not the same. So this is an example of a characteristic broken symmetry state of the old style. But there's actually no entanglement. I could assemble this by bringing atoms in for infinity and just lining them up in this way, right? So there's no particular entanglement across this boundary here. So if I cut it, I can just separate it and nothing happens. So if I did a measurement of this atom spin, it wouldn't affect the spin of the atom down here. And it turned out that what I discovered is that if the spin is integer rather, you've got a much more interesting state where, I don't know if I've got it on the next slide, I probably don't. You can think of the thing as the spin splits, and each of these atoms has like 2 hands, and you form a chain of people who link their hands together. And then at one end of the chain, there's one free hand that can wave around here, and at the other end of the chain, there's one person with a second free hand. So I've managed to, usually you'd say that the 2 arms of people that are joined to people, they're kind of connected. You've got a rule that as long as you didn't have an accident or something, the 2 arms always come in pairs, right? But by this trick of entangling the people, by forming a line where they hold hands, you can actually have a free hand that can wave around without a local partner to go with it, because the local partner was fixed by grabbing the neighbor's hand. And this is actually first of all, this entanglement spreads across the system, and then you've got these free half-integer spins at the end of the chain, which was something pretty unexpected. And you can see if I actually break the system, if I pull the 2 hands apart, I end up with 2 hands on the end of the spin, right? So this is actually, of course, it sounds very simple, but this was a challenge because it actually fundamentally involves a state with entanglement spread across the system, which wasn't a feature of the earlier thing. No one had thought that you had to worry about entanglement, and of course, I didn't know it was entanglement. But so this was actually, as I say, it's an extremely trivial-looking observation, but it was incredibly controversial because it actually challenged a view of magnetism that had been accepted for a long time, and no one believed that anything should be different between integer spin and half-integer spin. It turns out this is a special property and half-integer spins behave differently. This kind of state requires 2, right? If the spins, there's only 1 hand around, you couldn't form a chain where everyone joined hands. You have to have 2 hands to form a chain of people to link together. And this was thought significant enough that they put the picture of that thing on everyone gets a little kind of diploma on one side, some stuff about in Swedish about whatever it was, and then an artist's impression. The theme was doors opening to an unknown world was the theme of this prize, and each of us got a different thing opened up behind the door related to what their work was. So let me just briefly talk about the other effect, the quantum Hall effect. And again, this is a thing where you have a current flowing through something, and the Hall effect is if you measure the voltage drop across the place where the current's flowing, you can tell if the electrons are, what's moving. This is the way you know that electrons are the usual thing that move in a metal, although one of the advances of quantum mechanics was to show the discovery of the hole, which is important for semiconductors. And this also takes a little bit of thinking to get your brain around this, because in a p-type semiconductor, what's moving is not an electron, it's the absence of an electron, a hole. Again, that's a very deep concept that's obvious, but took some understanding from the Pauli principle that you could have such a thing. So the amazing thing was they did a measurement of the Hall resistance. Von Klitzing discovered under certain conditions this thing in a high magnetic field. This number turned out to be fundamental constants, the relation to the Ohm's law. This is Ohm's law written backwards. I equals V over R, really. The conductivity was some fundamental constants involving Planck's constant and the electron charge, and in the first case a whole number and now a fraction. And so this was accurately quantized. In fact, this is going to be the foundation of the new system of units, which is going to be announced later this year at some international congress. The amp used to be defined by force between current carrying wires, and now we're going to define it through this. So this turned out to be, this was accurately quantized. Initially, people looked for, relativistic corrections. Does this depend on the electrons not moving fast? And it turns out to be a completely topological thing. And the only reason that can violate this is that the sides of the sample have to be big enough that you can't have quantum mechanical tunneling between the two. But that falls off exponentially. So the corrections to this are only due. So provided the distance between the sides of the sample is large enough on an atomic scale or whatever, then this is perfect, right? It's topological. And it turned out, it wasn't of course understood it was topological, but in retrospect, anything that involved whole numbers has to be topological, right? And the amazing thing was, this is the sample in which at least the fractional version of this effect was discovered. So clearly, someone doesn't look very kind of skilled with the soldering iron here, right? But basically, a sample like this could show this perfect effect because of this remarkable robustness of topology that so long as it doesn't have to be perfect, it just has to be good enough, right? And then this kind of thing can actually show things up. And a little bit about explaining what that is, I will probably skip, but basically the quantum mechanics says electrons, in high school chemistry, you learn you've got this set of orbitals in an atom, and the Pauli principle says you kind of populate them and you're allowed to put up and down in each orbital, which was how the periodic table gets explained. And the quantum Hall effect, in some sense, can be viewed as a big kind of atom. The basic thing is you've got a magnetic field, and if anyone's done from a little bit of physics, you kind of know that electrons in a magnetic field go around in little circular orbits. And the important thing is the center of the orbit. There's only a kind of certain number of independent ways to put the orbit in. But if I look at this thing, the energy is like a planet in the quantum mechanical view of the atom. The old one, the planetary orbits were cancelled here. There's only a certain set of radii of orbits. The energy is quantized, and there's an orbit of one size, an orbit of another size. And that leads to something like at atomic levels, instead of just being SPD with a few, there's actually a huge number of levels. The number of levels in number of states in each of these levels is proportional to the size of the system. Depends on how big a box these electrons are moving around in. And the quantum Hall effect had the initial, and when you count the number of things, if you actually fill one of these orbital levels completely, like in an atom, you actually, of course, find an energy gap to the next. And it looks like you've explained the quantum Hall effect. If exactly n orbitals are occupied completely, you'll get the right relation between the electron density and magnetic field to explain the quantum Hall effect. But this can't be the possible explanation, because as I change the magnetic field, the number of levels changes. So there will only be exactly precisely one magnetic field at which this could happen. While von Klitzing discovered his effect because he was wise enough he designed his experiment not to switch on the current with the field in place, where he'd have never got to exactly the same current. He'd have always got a slightly different one. he switched on the field with a constant current in place and a digital voltmeter. And the digital voltmeter ended up reading the same number to some. So first they thought the digital voltmeter had to be a bad one because it kept coming to the same number of significant figures. It was like, and it turned out, of course, it wasn't, and the numbers were significant. So the topology is what means that the magnetic field didn't have to be fine-tuned. And in fact, it was only later that this was learned, really understood to be topological. If I put the system in a box, then inside the box the electrons go around in little circles, but some of the circles near the edge of the box, they're going to hit the walls of the box and bounce back. And instead of going around in a clockwise orbit, you'll find that the ones at the boundary kind of go around in an anti-clockwise hopping motion, skipping motion. And the energy is changed because the ones in the box have a nicely quantized energy, but since they only go around half, their kind of energy gets messed up. So as you go in the box, the energy levels aren't just straight like this. That they get to the end, counting from the center of the box, they start to bend upwards. And the highest level that's filled is called the Fermi level. And basically you can see that there's going to be a gap in the middle of the box wherever the Fermi, if you can change the Fermi level, it's going to influence the boundary, but not the center of the box. So again, this is the first indication that this actually was a topological effect, and it's associated with this very characteristic feature of boundaries. In fact, one of the co-people, one of the two co-laureates, he did two things. One of the things is related to this, that he came up with a beautiful calculation that obviously I can't go into, but again, toy models. It turned out the realistic system, you've got some dirt in the system, and it's all messy. It's not a perfectly clean box. But theorists like to work with things they can actually solve, and he studied the problem of a nicely periodic potential in the box, which is completely unrealistic, but is in principle similar. And he found out of this a formula. He found a formula for the whole thing, which turns out to be mathematically related, essentially a generalization of the Gauss-Bonnet formula I showed. So the Gauss-Bonnet formula got generalized by mathematicians in a much more abstract way, where the curvature became not the physical curvature of a donut, but a more abstract curvature, this one called the Berry curvature. But mathematically, it's some curvature and some surface, and the donuts are kind of, the real issue is not real donuts or any shape like that, but mathematically this is totally equivalent to what the explanation of all this stuff using donuts and coffee cups. And this formula that they found, and then it took as I say, it was in retrospect, so this explained it. And in fact, the other thing I probably described the other day was the final piece of the thing that really unleashed the topological revolution many years later was that you could do this without a magnetic field, and I described that yesterday. Amazing things. So this system has stuff that goes around the edges without, in one way, just like these skipping orbits. It's turned out you can do the same thing with light in photonic crystals and make these topological states and have put a boundary in the way, and stuff still goes one way around the edges. Topological insulators, all kinds of stuff here. Fractional Hall-Effect is where we have our great hopes for storing quantum information. I'll just show you one picture. Quantum Hall-Effect, let me go to this picture here, right? So in fact, this is an image of what people are hoping to store quantum information in. This is something where this is a quantum Hall effect, fractional, but in fact now people are trying to do this with other indium wires. You've probably heard of Majoranas, was a big thing a few years ago, was claimed discovery of Majorana edge states. These are like edge states of Majoranas, and so I make some defect in these states, and it turns out that you can store. It looks like I've just got 4 things here. They're actually 4 places where a quarter of an electron is charged. It's, again, this funny fractionalization. And quantum mechanically, there's a hidden degree of freedom in this 4 quasi-particle system of a non-abelian quantum Hall state that is hidden in there. You can entangle these things in 2 different ways, and I've chosen this has got some kind of, this is on the surface of a sphere, so it's got some tetrahedral symmetry, so I've chosen two particular symmetry combinations. So when you look at it, without detail, you see there's kind of 4 blobs there, which all contain a quarter of an electron. But the two, if you entangle them in one way, there's a very tiny little wiggly pattern that's different for the two ways of entangling it. And I can take quantum mechanics, I can take a linear combination of those states, and then the pattern changes. But as you pull these things apart, these little wiggles get exponentially small, and when they're far apart from each other, they're imperceptible. So the big problem of destruction of the information is if a cosmic ray or something passes through, or a piece of, then it could in principle behave differently depending on the wiggle pattern, and that would measure it in some way. But so once these things are spread out, the information which is vaguely hidden in this little wiggle pattern is become spread out all over the system, and damaging it at one place can't affect it. And so this is an example of the thing where the hiding of information in the pattern of entanglement inside the system. This is a dream for the topological quantum computer. And as I say, there's all kinds of amazing things that keep getting discovered in this area. People have gone on, or it started off, my work's got a little piece of it, but somehow it opened up a floodgate of people looking at this stuff, and all kinds of great things being found by lots of people. So they're all going to be, my bet for the next Nobel Prize in this area would be if this stuff if one can actually demonstrate this hiding of quantum information and maybe manipulating it, that would be an incredibly exciting experimental development, and a lot of people are trying to do this right now. And so anyway, there's a lot of things going on. I can't go into everything, but I would say, the whole catalogue of things, I would just say there's a lot more in this, and there's a great future, and who knows what the future is, of course, difficult to predict. As the baseball star, I forget his name in America, is supposed to have said it's hard to, what you predict, well, the future is hard. It's hard to make a prediction. But we can predict about the past, but not the future. But as I say, this stuff has opened up, and it's certainly become an intellectually very exciting area, and lots of young people have got excited about topology, and a number of seminars where you see the coffee cup and the donuts turning into each other. I mean, I said, please at least show the loving cup, right? Well, thank you.